Hello there, Mr. Sutton here with the AB Calculus Chapter 6 Quiz 3 Review Solutions on area and volume. For this problem, we want to figure out the area of the region bounded by these curves. So let me start by graphing these out. And I'm not really sure what window to use, so I'm just going to do Zoom 6 and hope for the best here. So there's the first one, and here is g of x. So I've got this bounded region in here that I need to figure out the area of. So taking a look at this, it looks like I can find this area if I just go from left to right and do top minus bottom. I just have one top curve, one bottom curve. All I need to do is figure out my limits of integration by seeing where these two things intersect. So where does f of x equal g of x? Well, let me use intersect on my calculator to figure this out. So to do this, I'm going to do second trace and intersect, and enter, enter, enter. Near the first one, it looks like we have an intersection at x equals 0. And then let me do that again. Second trace intersect, move over to the other crossing point, enter, 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 and that intersects at 3. So at x equals 0 and x equals 3. Now, if you didn't have a calculator, you could figure this out by setting these equal to each other and solving for x. And if you got something crazy like a decimal that you had to round off, I would store that as a constant both on your paper and on your calculator so you could bring it back for later. But we lucked out here. We just got 0 and 3. So then the area is just going to be the integral from 0 to 3 of, and now we have to do top minus bottom. So the top here, that's the negative parabola. That's the g function. The bottom is this f of x function. So we've got g of x minus f of x dx, and let's use the calculator to figure this out. So here's what this looks like on the calculator. I did math 9 to get my integral, going from 0 to 3, and if I want to do g of x minus f of x, I have to do y2 minus y1, because that's where I stored each of those. Press enter, with a dx there, press enter, and 9. Well, that's a nice round number. On this problem, I want to find the area enclosed by these two curves. Now, these are both expressed in terms of y, so in order to graph these, I'm going to want to use my draw function on the grapher. Even before I do that, though, I'm actually going to rewrite these in terms of x in my y equals. Even though this is not the same function, y equals x squared and x equals y squared are not exactly the same function, they behave in kind of the same way. It's just all the x and the y values are reversed, are swapped. So now let me quit out of this, and actually let me do Zoom 6. So here's the non-sideways version of these functions. We're actually going to come back to this graph to find intersection points in a little bit. But for now, let me go back to y equals and deselect these because I don't really want to graph them. And now quit out of there. And now I'm going to do second program to get my draw menu. And option 8 gives me draw inverse. Now I can just put in alpha trace y1. And that's going to draw y squared instead of x squared, because that's what draw inverse does. It replaces x's with y's. And we see that this is a sideways parabola. Now let's go back, and let me do second. Actually, let me just arrow up to this input from earlier. And instead of y1, I'm going to do alpha trace y2. And here's a line. I mean, it's a sideways line, but it's still a line. All right, so this is the picture we're dealing with. And it becomes very clear looking at this picture that it's going to be much easier to integrate sideways here. Because if we go sideways, we've just got one rightmost function and one leftmost function. If I'm going vertically, then I have a different top and bottom after I get to, looks like about x equals 1. So that's going to be kind of annoying. The good news is, if you want to go sideways with integrating, you need everything expressed in terms of y, which these functions actually already are. So this is kind of set up for us to do sideways integration. One thing we do need to figure out, though, is where these intersect. We need a lower y value and an upper y value where they intersect. And that's a little tricky because on the calculator, you can't interact with drawings, only with graphs you've actually done in y equals. So I'm actually going to go back to my calculator, and I'm going to go back, let's see, I'm going to go quit out of here. I'm going to go to my draw menu, and I'm going to clear my drawings out of there because I don't need to see them anymore. I am going to go back to my y equals now, and I'm actually going to graph y equals x squared and y equals x plus 2. If you want to find out the y values where these functions intersect, you actually just need to figure out the x values where these intersect. They behave the same way in terms of places that they equal each other. So let me go on that graph. I'll do zoom 6 again. So there's my parabola. There's my line. And now let me do second trace, option 5 for intersect. And let me do this one on the left here. Enter, enter, enter. Intersection is -1. That means we really have an intersection of y equals -1 down here. Now let me do this again to find my other intersection point. So second trace, option 5. Moving over, my little spider moves over to this one. Enter, enter, enter. They say x equals 2. That means we have really y equals 2, which it kind of looks like off of this graph here. So these equal each other. F of y and g of y equal each other at y equals -1 and +2. My area then is just going to be the integral from -1 to +2. So these are all y values now of, well, I need to do right minus left, more positive minus less positive. So the rightmost function, that was this g of y function. Leftmost function was the sideways parabola, y squared. So I've got g of y minus f of y. And then don't forget to make this dy because you're doing everything with respect to y. Now let me plug this in the calculator. Now the nice thing about your calculator is that when you're actually integrating this on here, you can do all of this with x's instead of y's as long as it's algebraically the same. As long as you're doing x squared instead of y squared and x plus 2. So let me just do, this was actually, I stored something that had this pattern in y1, and this was y2 that had this pattern here. So I'm going to do alpha trace y2 minus alpha trace y1. And this is really doing y plus 2 minus y squared, even though it looks like x is on the calculator. And then I'll make my dy, this will actually be a dx here, so that my calculator reads everything the same way. Enter, and it comes out to 4.5. For this problem, I want the area of the region bounded by these curves. So I've got a square root function, a line, and a horizontal line. Let me graph all these now. Not really sure what to make my window on these, so let me just zoom 6 this thing, and we'll see what we get. So there's my square root, my line, and my other line. Actually, I can zoom in a little bit. Let me do zoom 4. That gets me a little bit closer. So we see that we have this nice little bounded region right in here that we're trying to figure out the area of. And in order to do this, you have to consider, do I want to go left to right or bottom to top? Do I want to integrate vertically or integrate horizontally? If I integrate vertically, then my bottom function is going to change right about here. It looks like about x equals 3. That changes. So you're going to need two separate integrals if you're doing this with respect to x. If you're doing this with respect to y, then you only have one left function and one right function, and it's just a single integral. Just to get a little more practice with respect to y, I'm going to do all of this with respect to y. The only catch is, in order to do that, I need to rewrite all of these in terms of y. So I'm just going to isolate x in each of them. For this first one, I can subtract 1 and square both sides. So I can write, I'm just going to call this f of y equals y minus 1 quantity squared. For this other one, to isolate x, this is even easier. I just have to add 1 over here. So I can say g of y equals y plus 1. And now I can actually talk about these functions quickly. So let me go ahead now and set up my integral. Actually, before I can do that, I need limits of integration. We know that if we're going from bottom to top, the bottom is just 2, because they gave us the horizontal line y equals 2. But how about the top here? What's this intersection point? It kind of looks like y equals 3, but I'm not really sure. If you're not sure, then you could set these things equal to each other. And actually, what are we setting equal? Yeah, it would be the line and the square root function. Or, if you've got a graphing calculator available, we can actually just find the intersection with these things already graphed in terms of x. That's what I'm going to do, actually. Let me go to my calculator. I'm going to do second trace, option 5, intersect. And let's see here, move my spider up here, because this is the intersection I want. Enter. And it looks like I'm already on this curve, so enter again, and enter one more time, and we get an intersection of 4, 3. Now remember, I'm doing y values for this, so I just want the y value 3 out of this. I don't really care about the x value there. So we can say that these intersect at y equals 3. So my area then is going to be the integral from 2 to 3 of, and now I have to do right minus left. The right function is this sideways linear function, g of y. The left function is my square root turned into a sideways parabola sort of thing, f of y. So I'm doing g of y minus f of y dy. And now I need the calculator. So to do this on the calculator, there isn't really a quick shortcut I can take on this. I could enter these in my y equals and use that, or I could just enter them directly into the integral. I'm just going to do them directly, press enter, and I get about 1.167. On this problem, I want to find the volume of the solid obtained by rotating the region between these curves about the x-axis. Let me just graph this out to see what I'm looking at. So I've got the square root of x in my y equals. Let me zoom 6 that. And let me also graph this vertical line, which I can do by going to second program, which is give me the draw menu. Vertical is option 4. And then just put in the x value, so x equals 6. And there's a picture of what we're trying to revolve. So we're trying to take this region in here and revolve this around the x-axis. Now, it's crucial to note here that since one of the boundaries of my bounded region is the axis of revolution, the thing we're revolving around, that means that I can just use pancakes or disks for my cross-section of my area. So my area that I'm going to find and then integrate, I'm going to say a of x equals pi r squared to start with. We're just using circles. We don't need to use those donuts. And then the r value, the radius, that's just the distance from your axis of revolution to the other boundary here, which is given by just the f of x function. This tells you how far above you are from this function, from the x-axis. So I'm just going to write this as pi times f of x quantity squared. And for my integral now that I'm going to plug in the calculator, my volume, I'm going to have the integral from 0 to 6, just the limits of the bounded region. And I'm just going to be integrating my area formula that I just came up with. So this is just going to be a of x dx in here. And now for the calculator. Just to be a little bit fancy, I'm actually going to do a little bit of work in my y equals. In y2, I'm going to basically put my area formula here, which is pi times y1, the square root function squared. I could just say pi x, but I'm being fancy. Because you could do that with any function, even if it isn't easy to square. So now let me do math 9. I'm going from 0 to 6 on this. And then alpha trace y2, that's where my area function is, dx, grand total of 56.549. On this problem, we want the volume obtained by rotating this bounded region about the x-axis. So let me start by graphing this out. So I've got things entered in my y equals here. Let me go ahead and do a zoom 4 on this one. I don't think I have to go too far out to see where these intersect. So I've got this nice little bounded region in here. And nothing totally suspicious about this except for the fact that when I rotate this over the x-axis here, you'll notice there's a little sliver of space between the axis of revolution and the bounded region itself. So for that reason, we're going to have to use washers. So my formula then for my area of my cross-sections is going to be a of x equals pi times big R squared minus little r squared. Big R is the distance from the axis of revolution to the further away part of the bounded region. So that's going to be a distance of 2 to go from 0 to 2. So we've got pi times 2 squared. And then for my little radius, that's going to be how far the axis of revolution is from the closer part of the bounded region, which I can compute by just doing x to the 4th minus 0, or just simply x to the 4th. So I'm doing minus x to the 4th squared. And I'm just going to call that f of x in there. I mean, it already has a name, so why plug things in unnecessarily? All right, now I need to put this in an integral. I'm going to integrate all this from, let's see here, where are we meeting? Wherever x to the 4th and 2 match up. So I'm going to actually set x to the 4th and 2 equal to each other. And I could do this on a calculator and get a decimal, but if you think about this now, when we square root both sides, actually I should say when we fourth root both sides, since it's an even root, we're going to have a plus or minus. This is just going to be plus or minus the fourth root of 2, or 2 to the 1/4 if you want. So now my integral, I'm going to be doing the integral from negative fourth root of 2 to positive fourth root of 2 of, well, just this a of x formula that I just came up with. So a of x dx. Time for the calculator. So in my y equals, I actually defined a third function, y3, just to be this area function here, pi times essentially 4 minus f of x squared. So I just did y1 squared there. And now when I plug all of this in the integral function, so math 9, negative 4th root of 2, positive 4th root of 2, and by the way, if you're wondering where I got that special root from, it's in the math menu here. It's option 5. So going back there, I did alpha trace to get y3 dx, and that all comes out to about 26.567. On this problem, I want to take the region bounded by these functions or curves and rotate it around the line x equals negative 3. So let me get a graph first of all. I'm going to start by just graphing the line y equals 1 because I can do that right out of my y equals. And I'll just do a math or a zoom 4 on this one. I don't think I'm going to have to go too far out. But now to get this other one, square root of y, I'm going to have to use my draw menu. So let me do a second program here to get the draw menu. Option 8, draw inverse. And then I'm just going to do square root of x because then it's going to just turn around and do square root of y when it actually draws the picture. So there is what this radical y looks like. So we've got this bounded region in here. They also said x equals 0, so we've also got this bounded region here. And then x equals negative 3 is our axis of revolution. I'm just going to draw that on here. And now, so I have to take this region and spin it around something all the way over here. Because there's clearly a whole lot of space between our bounded region and our axis of revolution, we're going to need to use washers for this one. And because we have this defined in terms of y and we're going around a vertical line, going horizontally, I'm going to have to integrate with respect to y. So I'm going to write a of y equals pi big R squared minus little r squared. Big R, in this case, is the distance between my axis of revolution and the further away part of the bounded region. That's going to be square root of y minus negative 3, or radical y plus 3. So I'm going to square that, and I still have that pi out in front as well. Now for my little radius, that's the distance between the closer part of the bounded region and the axis of revolution. So that's just 0 to negative 3, which is a distance of 3. So we've got 3 squared that we're subtracting there. Now for my integral, my volume, I'm going to be going from the y value 0 to the y value 1. We're just going bottom to top. And I'm just going to integrate this a of y function, and I'll make sure I put dy in there as well. So let me use the calculator for this. So I'm going to do the bulk of the heavy calculator lifting in my y equals. I went to y2, and I essentially put in my area formula here. So pi, and then we had radical. This is radical y in disguise. I'm going to do dx in my integral, so my calculator treats this just like I'm treating it on paper here. And then, let's see, 3 squared is 9. Let me get out of there. And now I'll do math 9, integral from 0 to 1. And I'll do alpha trace y2 dx. And that's going to come out to how much? 14.137. On this problem, we want to find the volume described here. So they're telling us the base of a solid is the region enclosed by the semicircle of radical 81 minus x squared and the x-axis. Cross-sections perpendicular to the x-axis are squares. So we have to find the area of the cross-section on this one, the squares. So that's going to be, let's see, a of x equals s squared. And then the base of this square is just going to be the distance between the x-axis and this other function. So that's just a distance of radical 81 minus x squared that we're squaring. Now I also need an integral, and I need limits of integration. The limits of integration are just going to be where this function and the x-axis intersect. So that's going to happen at positive and negative 9 if you do all the algebra here. So now I have the integral from negative to positive 9 of this a of x dx that I just came up with. Let me use the calculator for the rest of it. So I did a fair amount of work in my y equals. For y1, I put the original function here, the original square root semicircle function. And then for y2, this is just my area formula where I'm squaring that first thing. So I'm going to do math 9 now, integral from negative 9 to positive 9. And then alpha trace y2 is where I put my area function. So dx, 972. For this problem, we have the base of a solid being enclosed by negative x squared plus 9 and y equals 0, the x-axis. Now our cross-sections, perpendicular to the x-axis, are rectangles, with height 6 times that of the side in the xy plane. So to get the volume of the solid whose base is this thing here. We essentially have to get our cross-section area and integrate it from, let's see here, these things are going to intersect probably at negative and positive 3, but we'll get there when we get there. Let's start with the area of the cross-section. We've got a of x equals, since it's rectangles, base times height. And we need to get everything in terms of the base before we can figure out, what this is in terms of x. So we have heights 6 times that of the side in the xy plane. So basically the height is 6 times the base. This is then 6b squared. And the base of one of these rectangles is just going to be the vertical distance between this function and this other function, which is just a distance given by negative x squared plus 9. I mean, you could do this minus 0, but it's just this. So we've got 6 times this stuff squared. And this is what I'm about to integrate now, but I need my limits of integration. So let me set these two functions equal to each other. And when I do that, if I add x squared to the other side and square root, I do have plus or minus 3 for the bounds of my region here. So for my volume, I've got the integral from negative to positive 3 of this area formula that I just wrote. Now for the calculator. So to do this on the calculator, I like to break things into pieces. I put this negative x squared plus 9 piece in y1, and then I just did 6 times y1 squared to do the 6b squared over here. Didn't have to, but I did. Let me get out of here now and math 9 this thing to get an integral. So we're going from negative 3 to positive 3. Alpha trace y2, because that's where the area function is. And then dx gives me an answer of about 1,555.2. On this problem, the base of a solid is the region enclosed by this semicircle here and the x-axis. Cross-sections perpendicular to the y-axis are semicircles. All right, well, this is a game changer. We have semicircles inside semicircles. Let me get the area of the cross-section, this semicircle here. So in general, I'm going to say a of y, because we're going with respect to the y-axis now. A of y equals 1/2 pi r squared. That's just general area for a semicircle. Now the radius on this one is going to be half the distance between this semicircle and the y-axis. And you can think of the semicircle as like a sideways kind of thing. You could even graph it out if you wanted to. But we need to go half the distance to get the radius. So I'm going to write 1/2 pi times all of this stuff divided by 2, or 1/2 times all of that stuff there. So note that I have half of that stuff, and then I'm squaring outside that parentheses. So the 1/2 is along for this squaring here. It is part of the radius that's being squared. All right, limits of integration. Let me just set this equal to 0, because that's what x equals at the y-axis. And I can see here just kind of guessing and checking that I'm going to get plus or minus 4 for those limits of integration for those y values. If you wanted, you could square both sides, add y squared, and then square root 16. So my integral then, I'm going from negative 4 to positive 4, and I'm using just this a of y that I just wrote with a dy. Let me call that a of y. There we go. Glad I caught that. So now we have to do this on the calculator. So this one is kind of nasty to try to enter in the calculator. I put this semicircle 16 minus x squared, although that's really corresponding to y squared, in y1. And then I'm just doing 1/2 times pi times half of that thing inside a squared parentheses. Quitting out of there, let me do math 9 for the integral. We're going from negative to positive 4. And I've got alpha trace y2 for this, dx. And that should come out to 33.510.